Yeah, so good afternoon, everyone. So as we already have been introduced, I'm Florian, and this is my colleague Štěpán. We work at Oracle Labs. So we are software engineers there, and we are in the Graal team. In particular, we work on GraalPython, which is a Java-based implementation of Python. And we are also HPy co-developers. So we weren't in the group of the HPy founders, but we joined very early, so we were there since almost at the beginning. So this talk is about HPy and tries to motivate HPy and introduces it. And also we try to show you the benefits of it. And in the end, we want to convince you to use it. So what do I expect, or what do we expect from the audience? I mean, it's not strictly necessary, but we think it's beneficial if you are an experienced programmer, Python programmer, maybe even wrote C extensions. You should know C a little bit and the memory model and so on, and have some vague understanding of the CPython internals and how the CPython header look like. But I think that the previous talks made a good impression on that, so I think that should be fine. So let me quickly try to motivate HPy. So CPython, as we already heard this day, is the reference implementation for Python, and it is a bytecode interpreter written in C. So there are several alternative runtimes, for example, GraalPy, PyPy, Python. You may know some of these. And most of them try to improve Python execution speed by using some optimization, like using a cheat compiler, having some different data structures, using a moving GC. And as it turns out, some of those projects were pretty successful in doing so. So for example, here is a chart where we run the performance benchmark on GraalPython, and we are on average 4.x times faster than CPython, most notably compared to CPython version 3.10. So the newest optimizations from Mark are not included yet. But yeah, and I need to note that the Python performance benchmark only contains Python code as far as I know. So the Python C API, since Python became very popular and also numerical computation started to use it, it quickly turns out that Python performance is maybe not sufficient. So the first C extensions appeared because since CPython is also written in C, that's a perfect fit, right? So CPython kind of started to allow C extensions, and there was not really a design phase to do so. So what happened is that C extensions used the existing APIs, and there are some problematic points with the C API as it exists. So for example, it exposes, or most notably exposes, a lot of implementation details, as we heard already today. So for example, it exposes data structures, fields of data structures. It exposes reference counting. The lifetime of objects is managed by using reference counting. It exposes that objects are referred to as C pointers, which means that you know the memory location of objects and you can defer further assumptions. And all this is happening in C extensions. And that makes it very hard for alternative runtimes to implement and to support C extensions. So at this point, I want to refer to Victor Stinner's PEP 620, which really nicely summarizes a lot of problems. So let's just pick one example of a problem, so reference counting. Since GraalPy is written in Java, and Java has the most advanced and mature GC implementations, it's really bad that we can't really use, use our GC and do optimization or like do its proper work on C extensions, because reference counting is basically preventing the Java GC to be used. Since reference counting means you to a certain degree you do manual management of the lifecycle, and the GC then cannot collect the garbage, since you need to define when it's collectible. The GC is not only about collecting garbage, it's also a memory manager, basically. So state-of-the-art garbage collectors can do super fast allocations, can do super fast deallocations. They have minimal to no pauses, of the application and can make use of multi-threading. So the question is now, why should you as a user care about this? And for this, I have one number for you. So there's the gcbench.py, which is kind of a benchmark for the GC. And GraalPython is, on this one, 79 times faster than CPython. And also, most notably, PyPy is also 25x faster. So it does make sense to have alternative implementations that can do stuff at some point a little bit better, maybe. Okay, so let's now switch to HPy. HPy is a novel C API for writing C extensions. You basically do, instead of include python.h, you include hpy.h. It's funded, the project is funded directly or indirectly via Open Collective, Oracle, IBM, Quonsite, and Anaconda. And HPy tries to be a more abstract API. It tries to hide the implementation details. It aims to be faster on alternative runtimes and aims to be easier to implement on alternative runtimes. And also a dedicated goal is to be GC friendly. So we as a HPy co-developers defined a list of goals. So HPy should have 0 overhead on CPython, because we know if just by switching to HPy there is a performance penalty, you won't use it. So we really try hard to fulfill this goal and to reduce the burden of switching to HPy. Also, there needs to be an incremental migration path, because if we know that porting one big C extension at once to HPy is almost impossible and very error prone. So you would also just give up on that, I guess. So HPy tries to be fast on alternative runtimes, as mentioned. HPy wants to provide a better debugging experience, and a very important goal is HPy provides the universal API, which allows you to build one binary that can run on multiple interpreters. And the other way around, we also provide backwards compatibility, which means you can run different HPy versions in the same interpreter. Okay, so how does HPy look? It's very simple. I hope you can read the example. So you start by just including hpy.h instead of python.h, as I mentioned. And then here we write a very simple C function that just creates a Python Unicode string out of a C string and returns it. So in HPy, we use some, let's say, sugar to define all the methods. Here it's a macro called hpy-def-meth, which defines that there should be a method called, and the Python attribute is called sayHello. It takes no arguments. The implementation is by a convention, sayHello_impl. And then we just need to register to the list of methods and to the module. In the end, you use another macro to generate the module in it, and that's it. So very similar to C API, and that's by intention, of course. So on the other side, you see a little setup.py, how to build HPy. So it's basically the difference here is that instead of using X modules, you register to HPyX modules, and you need to depend, unfortunately, to HPy. At some point, if CPython maybe takes over HPy, then you can maybe just drop that. But let's see. So then in the end, you can just build, run this setup.py, and there is an additional option now available where you can choose the API mode you want to compile for. Okay, so how do we reach the 0 overhead on CPython? There are multiple compilation modes, and so the first or the most important one is the universal API, which means, as I already mentioned, you can build one binary for multiple interpreters. This works by having a HPy context, which is kind of a function table, and you do all the calls indirectly through this context. So this would be the path from here. You have your extension, you compile for the universal API, then we have our own API tag, and then you can run on the different interpreters. So HPy also provides custom APIs. Custom API means we map HPy API functions to interpreter-specific API functions. So for example, we did that for CPython API already, which means we map HPy API calls to C API functions of CPython. So like HPy Unicode from string will be Py Unicode from string. So there is no runtime overhead involved then in the end. It's just a compile time dependency. And this would, just to show you the path, you compile your extension in this mode, and then you get a CPython specific shared library. And you can only run, or usually you can only run this on the one interpreter. And in theory, but that's not implemented yet, you can have APIs for other Pythons as well, like Rust Python. There has been some work on that, but it's not finished yet. So last but not least, there is the hybrid API, which is used to, which is the mode you use when you do incremental migration. This means that you already use HPy, but still have some C API function calls since you're incrementally migrating to HPy. Okay, so how does the incremental migration work? So this is just sketching the progress you usually do. You start by converting your module definition to an HPy module definition, and that's very similar. So it's really just, instead of Py module def, you use HPy module def, you fill your fields, and you keep your functions, your legacy functions, so that's how it looks in C API, just as a legacy methods here in the definition, and that's the first step, basically. Then you already create an HPy module, but using legacy API, and then you can continue with migrating the types to HPy types, which is very similar. You translate your Py type spec to an HPy type spec, and again, keep your functions as legacy methods and slots and members. While doing so, you can always communicate with, or always use the legacy code as well by using these conversion functions, HPy as PyObject and HPy from PyObject. And after each step, you just build your extension with, in the hybrid API mode, and you can test your whole application after each step. Okay, so a few performance numbers. We already ported Kiwi Solver and did run their only benchmark, I think, which is the suggest value. And the blue line is the C API version, so like the original Kiwi Solver. And yeah, you see it's about 0.135. And in the CPython API mode, we are almost there. I mean, it's even a bit faster, but I wouldn't give too much on that because there is some measurements error going on, of course. So it's basically, I mean, the difference is very low. And then expectedly, the universal API is a bit slower, but it could also be just an error. But that already convinced us, or like gives us a good feeling that the CPython API mode is really the best, gives you the best performance on CPython. So we also did started to migrate NumPy and did some measurements there. It's not yet done, so there's still lots of benchmarks that use just C API, but some of those already use HPy, and this is an in-between step, but we are kind of observing that. So while we migrate NumPy, we look at the benchmarks, and here you see the CPython API mode, the median of all the benchmarks is almost at 1, which means it's basically as fast as the C API version. And in the hybrid API mode, which means we are doing the calls through another indirection, we are a bit slower, like 2%, and also the jitter is a bit higher. So, but that is already also a good outcome for us. So we will continue to work on NumPy. Okay, so a debug mode is the thing where we try to provide a better debugging experience, and it can also be called the strict mode. So it's an optional runtime mode which you enable at load time, basically, of the module. So you don't need to recompile anything. It strictly enforces the HPy contract and does additional bookkeeping of resources. So the goal is here to prevent unintentional misusage of the API, which happens to work on some interpreter because of some optimizations. And our debug mode is right now able to detect problems like leaked handles, usage after close, lifetime of data pointers, like if you get the data pointer of a bytes object. That's also read-only, so it checks also if you write into this, and you may also not store the HPy context somewhere and reuse it, and we also check it. So that's the mode where you test if your extension is ready for all interpreters. So the most useful function of the debug mode is the leak detector, I think. So I wrote here a simple example where we just create a Python integer from a C long, and then we just forget the close. And you can use the leak detector by importing leak detector from HPy debug, and then you run it as a context manager and just invoke your Python, your C extension. And then in the end, you get a HPy leak error because it detects, okay, you created a handle, but you never closed it. So that could be a problem. And if you enable the stack trace limit, then it will also show you the stack trace where this handle has been created. Okay, so let me, for the universal API, I want to quickly give a demo. So I hope this works nicely. So here we have, I built NumPy with, sorry, I don't have it on my screen. I built NumPy with Python 3.11 in the hybrid mode. And here we have, that's already GraalPython, sorry. I wanted to start with, again, sorry. Okay, so here I have 3.9, and I just run the Python, the hybrid, the 3.11 hybrid binary with some example where we know that we don't trigger any problematic code path for now, since it's, it's an intermediate step. So, and we can just run this binary on 3.9, and you also see that we really use the HPy 0, which is basically the HPy version, and CP 3.11. So we use the one we built with for 3.11. So we can do the same for Python 3.10. So it also uses the same path and uses the same binary, and it works. Then we can do that for 3.11, which is the one I built it for, of course. I mean, that's expected to work, right? And then, most notably, there is GraalPython, which is like our tool. And we can also run this here, hopefully. Yes. Okay. So that's already a bit impressive because we can now build one binary and use it on very different interpreters. I mean, GraalPython is a completely different implementation. So some words about NumPy, HPy. This one is a very hard one to migrate, of course, and we chose to do NumPy because we think if we can do NumPy, we can basically migrate any package to HPy. We already invested almost 1 year of a full-time equivalent employee, and yeah, NumPy is just huge. It has 180,000 lines of code using C. 80,000 lines of code of those are using the C API. Then we changed 40,000 lines of code already, and 15,000 lines of code are fully migrated to HPy. So there's still a lot of work to do. There is also, NumPy has its own C API, so you can use NumPy from other C extensions. And there are 261 functions or entries, and we migrated already 118, so it's roughly half. So still work to do, but we think the hardest part has already been done. We migrated most of the types, or at least the hardest ones. And for example, we needed the meta class support for heap types, and we were in the group of initiating that for CPython, which is, by the way, already now merged. So if you want to see our progress, please just check it out. It's all public on the HPy project. So what's the current status? HPy is currently at version 0.9. We partially migrated several different packages like UltraJSON, Matplotlib, PSUtils, Kivisolar, Pillow, PicoNumPy, which is an external contribution, and NumPy, as I mentioned. We also plan to have a Python backend We already created a proof of concept, and we will have a person working on that in the next half year, so I hope there is some real progress going on. So now I switch over to my colleague.
So I will say a bit about our future plans and about the HPy community. So right now we want to concentrate on the NumPy HPy work, and we want to do this step by step, working with the NumPy developers. And after that, and once we think we figured out everything, hopefully we will release our first release. Something about the community. Oh, wait a second. Florian, can you help me here? I'm not a native Mac user. Right. Yeah. So I was going to say, HPy lives on GitHub, and HPy itself is basically a CPython extension. We first developed the functionality for CPython, so basically we are doing this translation from the HPy API to the CPython API. So the work that people do in this repository is the design of the HPy API and then the implementation for CPython. So if you know how to develop CPython extensions, you can already just find your way around this repository, I would hope, and you can already contribute. There are issues there. There are some issues which can be quite suitable for like a startup tasks. We also have a documentation / landing page, but we are VM developers and compiler developers and so on. So we're not really good at web design and things like that. So that's also an area where we can use some contributions. And also, like it would be great to extend the set of people who contribute to the design of HPy with people from different and other Python implementations and from other bindings like Cython, PyBind 11, etc. Yeah. Right. Okay, how do I switch back to the slides?
Yeah, that's fine. Okay, so that's basically from our side. Thank you for your attention, and we're happy to take questions or give over to the session chair.
Thank you very much. We still have some minutes for questions, so please queue up. Maybe the first one in the back.
Hello. Yes. I actually have 2 questions. Sorry about that. I want to say this was really impressive. So thank you for that. That was not a question. And now the questions. When you have a single extension module that you can load in various interpreters, is there a runtime dependency on a package that is different, or is it compiled in? So like, for example, with zip that is used in PyQt and stuff like that, you would have a different extension modules with zip, and then other extensions modules would be universal and just use a different kind of that? Or is it a single non-dependency thingy and it includes all of the stuff?
So the C extension itself is self-contained usually. I mean, if the C extension links to some library, some I don't know, compression library, for example, then of course there is a dependency, but there is no runtime dependency to HPy, except of course on CPython, you need the HPy module to have installed, because in CPython, HPy itself is another C extension. So you just need to install HPy on CPython, that's it. So for GraalPython, for example, we have intrinsic support for HPy, so there is no dependency. So I hope that answers the questions.
I think it does, thank you. And the second question was, if you say you ported a large part of NumPy, Pillow, and other projects, has this been merged to the projects itself, or is it just like a fork for now for most of them?
For now, it's a fork. We plan to upstream that, but of course, I mean, these package authors want to have confidence that HPy is something that stays, and we are in the process of convincing and getting users. So yeah, right now it's in forks. It's public, but it's in forks. And for NumPy, we have really good support. So Matti is one of the NumPy co-developers. He's on our side, basically. And also Sebastian Berg, which is one of the co-developers, is very interested. But it's still a lot of work to do, right? I mean, getting all the benchmarks to stay at a good level and also getting the tests pass. Yeah, there's still a lot of work to do.
Thank you.
Thank you. Now in the front, please.
To what extent would it be possible to build tools to port CPython extensions to HPy, assuming that the CPython extensions are reasonably well behaved, because they can?
That's a good question. Yeah, I think, or we think that to a large extent you could automate the very simple, the boilerplate tasks. We already hired an intern that should have done a tool, but the one canceled in last minute. But we already planned to do so. So like a simple tool that would convert your module specification, that would convert your types, and everything it can do, and then something is left, of course, and then you need to manually fix up. So that would be the plan, and I think we can do a lot.
Maybe I would add that the very first step with the migration is like a migration to heap types, for example, or migration to multi-phase init module initialization. So some of the steps you have to take anyway if you kind of want to have your extension be based on a modern CPython APIs. And those steps are a bit harder to like automate, but you would kind of want to do them anyway.
Thank you.
We have a question also in the back.
So I wanted to ask how safe is it for a maintainer of package with C extensions to migrate to HPy right now? So should I wait until there's at least 0.9 final?
Probably yes. So yeah, we are going for stable release, of course, and I would wait for that. But I mean, you can start now and test. So about the safety, it's hard to tell. I mean, if no one ever is using HPy, it's hard to keep the project alive, of course. But I mean, we are working on it for 4 years right now, and it's still there. So I have confidence that it will stay. But and there is the risk is you could also switch back again, because you can generate from HPy, you could generate C API calls again, so you could just step back.
And yeah, maybe one thing I would add for the risks, there are like multiple projects involved in HPy, so I think that kind of should lower the risk factor. It's open source, it's on GitHub, so like we're trying to do as much as we can to lower the risk. And yeah, so we're aiming for some stable release, and at that point I would say it's safe to use, or should be safe to use. And at this point it would be very useful to get feedback.
Yes.
Thank you.
Thank you. Now we have a question in the front.
Hi, thank you for your talk. Maybe a very pragmatic question. So imagine you migrate NumPy to HPy, right? And I have a library that depends on NumPy, let's say something like pandas, and it's not yet migrated. Can I already switch out the dependency and get benefits from your work?
Yeah, how to answer? I mean, if your module is still on CPython, then you are kind of bound to those restrictions, right? You can use NumPy HPy because you can just have a little bit of glue code that would just do the conversion, as I showed. You can use this HPy as and from Py object, so they would just convert between those. Mm-hmm. But if pandas is not on HPy, it's hard to make use of all HPy benefits, right? You could still, I mean, that's still possible. You can use the debug mode for your dependency that is in HPy. So you can use debug mode in this case for NumPy and find some leaked handles. But you cannot use it, of course, for pandas. So partially, I would say, you can make use of the benefits, partially.
Okay, thank you.
We have the last 2 questions. First, I will read one that we have remote. It's how is the PEP 703 affecting HPY? So the no-GL PEP.
We discussed it a lot. So HPy always tries to be prepared for that. Since it's not yet implemented, it's hard for us to do anything. But yes, HPy should be, and we try to ensure that, should be ready for the no-GL PEP.
This is being recorded, you know. So.
Yeah, sorry, I'm not sure whether it can read.
Yeah,
okay, thank you very much.
Maybe I would just quickly add to that, because of the design of HPy, which is GC friendly and abstracts things, I think HPy would be actually, if CPython was using only HPy right now, and all the extensions were in HPy, this PEP would be in much better place, because they could do much better things, even implement GC instead of reference counting, which would be better with free threading.
As well.
Yeah, and for multiple interpreters as well.
So we have now the question in the back.
Yeah, hi. Thanks for the interesting talk. I would like to ask a maybe simple question. What do the H in the HPy name means?
Yeah, it's on the website, so I assume you didn't visit it so far. No, it means handle. It stands for handle. So it's handle Pi, basically.
So the core idea is that instead of Pi object star pointers to actual memory where the objects lie, you work with handles, and those are abstractions. You shouldn't be able to see through them into the implementation details.
So quickly, the last question.
Okay, thanks. I think you've answered this before probably, but just to clarify, with the GraalPy implementation, are you able to leverage the Java GC mechanisms, or are you locked into reference counting still?
So for HPy, no, we are not locked into reference counting. In HPy, we have, I didn't go into detail too much here, but we have another kind of handle, which is the HPy field, which you use if you store in your C structure some other object that is tied to the lifetime of the owner object, and that's something that the GC knows and can use. So yes, absolutely, we make use of it.
Okay, thank you.
Cool, so we are running out of time. I'm really sorry, but maybe you can catch them afterwards. I guess that you will be available during the conference, so if you have any other question, maybe you can ask them. So let's thank them again. Thank you.